Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the concept of simple linear regression. Let's start by talking about when to use simple regression. Simple linear regression is used when we have a numeric or continuous predictor variable, x, and a continuous outcome variable, y. When we say simple linear regression, we simply mean that we just have one predictor variable. If we had more than one predictor variable, we would do something called multiple regression. That'll be the next topic that we talk about. So because we have a continuous predictor and a continuous outcome, let's take a look at some examples of research questions we could ask where linear regression would be appropriate. For example, examining the length of time in therapy to see if that influences depression. We would have a continuous predictor, which would be time in therapy, and a continuous outcome variable, which would be depression, a depression scale. Another question we could ask would be if social support influences stress levels in college freshmen. Again, here we have a continuous predictor, which would be some social support scale, and some continuous outcome measure of stress. A third question we could ask would be, does GRE predict graduate school GPA? We know that GRE is a continuous and numeric variable, and we know that grad school GPA is also a continuous numeric variable. Let's take a look at the equation for simple linear regression. There are two parameters of interest to us. Remember that parameters are the population parameters that we are going to estimate. So there are two parameters we are going to estimate in a simple linear regression equation. And the two parameters that we're interested in are the intercept and the slope. Now I've highlighted in boxes here the different parts of the equation to show you how this maps on to the overall framework that we've used so far in this course. Here, y is the data, y sub I. That's the observed score on the outcome for every person. The model here is represented now by these two parameters, the intercept and the slope. The slope maps on to the single continuous predictor x. So x sub I is some score on the predictor variable for each person. And then we've got, of course, the leftover error. So the model portion of this equation within this framework is the intercept and then the slope multiplied by the continuous predictor. The interpretations of these parameters, the interpretation for the intercept is that the intercept is the predicted value of y when x is equal to 0. The interpretation of the slope parameter is that the slope parameter is the change in the outcome for every 1 unit increase in the predictor x. Let's take a look at an example. Say that we want to rent a Bird e-scooter to get across campus to get to our classes on time. Well, renting a Bird e-scooter costs $1 to activate and then 15 cents for every additional minute thereafter. We can actually frame this as a regression equation. Let's say that we want to predict a total cost, how much it's going to cost us to rent a Bird e-scooter. Well, we're going to have some intercept in this model, B0, and because renting a Bird e-scooter costs $1 to activate, our intercept is $1. And because the slope is the change in y for every 1 unit increase in x, if we frame x, the predictor, as time, then for every time in minutes, then for every minute, we know that we are going to increase the cost by 15 cents. Therefore, our slope would be 0.15. Now let's talk about these predicted values of y in the regression equation. When we substitute a predictor variable x score into the right side of the linear equation, this will give us some predicted outcome score. And we call this predicted outcome score y hat. Now, continuing on with this Bird e-scooter example, let's take a look at what the plot would look like if we were to plot cost and time for this model. So we have the general regression equation, and we plug in $1 for the intercept and $0.15 for the slope. The predicted value when x equals 0, or when time is equal to 0, is going to be 1. It's just going to be the intercept, or $1. So if the predicted value of y is 1, that's telling us that before we start riding the scooter, or at time equals 0, we are going to pay $1. The cost is going to be $1. Now, here is a plot with the slope highlighted for the predicted value when x is equal to 1. Now, if x is time in minutes, this would be for 1 minute after we've rented the Bird e-scooter. So now when we look at the equation, essentially we want to plug 1, the value for x, into this equation for time. And so we can see how we get this predicted value for y. We have the intercept, which is 1, and we have the slope, which is 0.15. So if time in minutes is equal to 1, we multiply this x value by the slope, 0.15, and this gives us a predicted value of 1.15. That is, predicted value of cost is going to be $1.15 if we have rented the Bird e-scooter for 1 minute. But let's say that we have to rent the e-scooter for about 5 minutes to get from point A to point B on campus. Well, we can predict how much this is going to cost us as well. What we do is we plug in 5 now for x, or time, and we multiply the slope, which is 0.15, by 5. And then we add that value to the intercept, and that gives us the predicted value of cost. We see that this predicted value of cost is 1.75. So this is basically telling us that we can predict that if we have to rent the Bird e-scooter for 5 minutes to get across campus, we're going to have to pay $1.75 to rent the scooter. Now, a general regression model for social sciences data typically includes some systematic component that's due to the predictor variable x. And these are the points that fall along the regression line. So essentially what that is saying is that as y increases, x systematically changes as well. In this plot on the right, we can see that the regression line going through the center of this scatter plot is telling us that as y increases, x increases as well, or as x increases, y systematically increases. We can also see that these scatter plots of the scatter plot of observed data, the data don't all fall perfectly along this line. So the systematic component is the regression line, and the leftover error is the difference between those dots on the scatter plot and the line. Now, y hat, again, is the predicted value of the outcome. And we know that the predicted value of the outcome is equal to the intercept plus the slope multiplied by the predictor. So we can actually plug that into this equation and see that the observed value for y is going to equal the predicted value for y, which are the points along this regression line, plus some error. Now, we'll get more into model comparison when we talk about null hypothesis significance testing. But basically, we can think about the null hypothesis model, or model C, as a model which only has some fixed value for y. That's to say that x and y are not systematically related in any way. So, for example, in this scatter plot on the left, we can see that the scatter plot looks completely random. There's no slope at all going through this scatter plot. So the values of x and y are not related in any way. We would not need x in a model of y. However, in this model on the right, which would be the alternative hypothesis model, essentially we need to incorporate x so that we can say that x somehow does predict y. On this scatter plot, it's clear that x and y are somehow systematically related. And so we need to account for x, or the independent variable, in this model. So model C, the compact model, or the null hypothesis model, essentially doesn't include x as a predictor at all. And the augmented model, or the regression model, also known as the alternative hypothesis model, does incorporate x as a predictor. This concludes the first lecture on simple regression. In the next lecture, I'll demonstrate simple regression with an example.